Hi guys, in this video I'm going to introduce the push down automata, which is what we get when we give a finite state machine some memory. I need you to remember two things for this video. Firstly, that we have a set of context-free languages that includes languages which are not regular and therefore which we cannot accept using a finite state machine. And I need you to remember the finite state machine formalism, particularly how we do the state transition diagrams. So I'm going to take you through this concept by doing a particular example. So that example is the first language that we came across where we realized we couldn't do it with a finite state machine, and that was A and Bn. So we know that one of the properties of all of the strings in A and Bn is that they match the regex A star, B star. So all of the A's come before all of the B's. And we know we can build a finite state machine to accept this bit because I just made a regex for it. So that finite state machine is pretty simple. We have a state where we accept the A's, and then we transition at some point over into a state where we accept B's. And we'll make this an epsilon transition and just leave it as a non-deterministic finite state machine for the moment. So this lets us filter out, in a sense, all of the strings that don't match the form of having all of the A's before all of the B's. But you can see that the one thing that the strings in A and Bn have that we can't do with this finite state machine is we know that all of the strings have the same number of A's as B's. We need some way of counting them, but because there is no limit to the size of the strings that we can accept, there is no single machine with a finite number of states that can accept that language. But what if we had a bucket? So that every time the machine saw an A while it was perusing through a string, it read the A and followed then transition, but then popped it in the bottom of into the bucket. Then when it sees the next A, it pops it into the bucket. The next A, it pops it into the bucket. Then, once we follow this transition over here and start seeing B's, for every B, we take an A out of the bucket and match it off. So that when we finish seeing the B's, if we have an empty bucket, then we can accept because we know that we had as many A's and B's, provided, of course, that we don't have any more B's at the end here. And if we run out of B's and the bucket is not empty, then we reject. So we can see with this data structure here added as a memory element to the finite state machine, we can now start dealing with languages that we couldn't manage before with finite state machines. Because the main thing with the finite state machine is we could only have a finite amount of memory in the structure, because the only memory that a finite state machine has is what state it is currently in. However, you can see with this formalism that doesn't matter how many A's we see, we can always chuck another one into the top of the bucket. Now in this case, you might have noticed that the bucket looks a lot like the stacks that you've learnt about in Sang 1120 in your data structures course. And that is because that is exactly what this is. So the idea of a push down automata is simply a finite state machine with a stack attached to it. So we can do stuff where we either push a certain number of things onto the stack, onto the top of the stack, or we can pop an arbitrary number of things off of the top of the stack. Now we'll see that in general the idea of arbitrarily giving memory to a finite state machine creates a bunch of different formalisms that all have different power. This particular one, where what we give it is a single stack, defines the set of machines that can accept the context-free languages. So, what we had for the finite state machines, in essence, was a finite set of states. And a special state where we always started, and a few special states, so a subset of all of the states where we can accept a string if we end up there with an empty string, and ways in which we can move between the states. And one of the important things was that each of these ways either uses an element from the alphabet or the empty string, epsilon. Push down automata are all the exact same first four things, but with an additional memory in the form of a single stack. So one of the key things is that some of these original aspects change slightly when we add the stack. So the finite bunch of states is still just a finite bunch of states. The special state where we always start is still just a single state in which we always start the machine. The few special states for accepting are still exactly the same, however, they will have a slightly different criteria for when they can accept, and that will depend on the presence of symbols on the stack. And the ways to move in between the states will be almost the same, in that they will still consume either one or no symbols off the front of the string, but they will also involve fiddling with the stack. So what this means on our state transition diagrams is where before we had transitions where we labeled them with one element from the input alphabet or epsilon, we now have a set of transitions with some extra information. So each transition gets labeled with something slash something slash something, and the first part is the exact same bit as before. So this bit here is still one element from sigma or epsilon, and it indicates what symbol has to be present at the start of the part of the string that we're looking at now in order to follow that transition. So if this transition here has an A at the start, then we can only take it if the current first symbol on the string is an A. The next two bits deal with the stack. What they are is the second part indicates what we pop off of the stack, and it may be 0 or many symbols. So before, in this first part, we can only have one symbol. In the bit where we pop and push onto the stacks, we will actually allow multiple symbols, because otherwise the size of our push down automata gets incredibly large. So here we can have something, and it will be in the form of an alphabet cleaned, and it indicates what we take off of the top of the stack when we follow that transition. So if we see this symbol and we follow the transition, then this bit here gets popped off of the stack first. Now that can be epsilon, so in the case of this very first transition, nothing gets taken off of the stack. The next bit is what we then push back on top of the stack. So we always pop before we push. And that again can be in the form of something to the clean. And when we go into the second video, you'll see exactly what is cleaned. But that is a set of symbols that we that is a string of symbols that we push in order onto the stack. Now often that'll just be one symbol, but sometimes it might be multiple, particularly when we have some interesting counting languages. And you can see here that in this case we're pushing a symbol at. That's one of the other interesting things, is when we may have a string that can only exist in this alphabet, input alphabet A, B, we can have a completely different alphabet, and this will be called the stack alphabet, and this is the set of symbols that we can push onto the stack. So you'll see that later that we can actually have a completely different stack alphabet, and sometimes that may be helpful for us when we're trying to do some counting problems, and sometimes it's not really helpful at all, because often you can do exactly what you want it to do if you just push elements from sigma onto the stack. But in this case I wanted to show that you can use other elements. So in this particular push down automata we have a stack, And whenever we take a transition where the first symbol in the string is an A, then it doesn't matter what's on the stack, we won't pop anything off of it, and we will push an at symbol onto the stack. So if we have the same string that we had before, A, B, 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 then we will go through seeing each of the A's and following that first transition, and we will push an at onto the stack. This transition here is the equivalent version of just the epsilon transition before. So this transition can be taken in any situation because it doesn't require there being anything on the front of the string. It doesn't require anything being on the top of the stack, and it won't push anything onto the stack. Then we're over in the accepting state Q1, and we start transitioning here only when we can see B's. So upon seeing a B, we must also see an at the top of the stack, otherwise this transition cannot be taken, and when we do, we will pop the at off of the stack. So now we're left with a stack with two ats. Now at no time can the machine know how much is left in the stack, it can only look at the top element of the stack. So it will follow that transition repeatedly, at least the next 2 times, because it can see ats at the top of the stack. And then when it arrives here in the accepting state, it will now have nothing left to see on the string. So with our finite state machines, we could accept when we got to an accepting state with an empty string. For our push down automata, we accept if we get to an accepting state with an empty string and an empty stack. So in this case, we can accept the string because there's an empty stack. Now, in the case that we had 4 A's followed by 3 B's, then we would still have 1 extra at sitting at the bottom of the stack because it wouldn't have been matched off by all of the B's. And therefore, when we hit here, we would not be able to follow this transition anymore to get rid of that at because we don't have any more B's in the string, but our stack would not be empty, so we would not accept. Conversely, if we had the string of 2 A's followed by 3 B's, then we would have pushed 2 at symbols onto the stack, and we would have popped both of them off of the stack, but we would then be sitting here in this state Q1, and we would still have a B on the front of the string, but we would not be able to take this important transition here because there is no longer an at symbol on the stack to match it with. So we said before, we have to be able to see this at the front of the string to be able to take the transition, and by the same token, we have to be able to see whatever we're going to pop off of the stack in order to follow that transition. So in this case, we would be stuck here in Q1 with no transition that we can take to get rid of the rest of the string, and so it would halt and reject. I know that video was a fairly small number of slides with some fairly long-winded explanations. If you aren't particularly comfortable with push down automata, there's a couple of more videos to watch, and then you've also got the lectures and tutorial materials. But the key difference really is just that you have exactly what you have with a finite state machine, but you also have this stack. So our transitions between states will involve modifying the stack by taking elements off of it or putting more elements onto it, and accepting depends on the stack being empty or not. So the things you should know from this video is you should have an awareness of push down automata, but only in the form of the state transition diagrams. The next video will talk about the formal definition. And you should be aware of how the operation of a push down automata differs from that of an FSM. And that's what I was saying before, just how the transitions change and how we modify the definition of accepting when we have a stack.